Alright, so can you guys see my screen now?
Yes, sir.
Okay, and also just give me a thumbs up. So just to let me know that you guys are already in front of your computer. Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, so maybe at least half of you are already here. Anyway, so the others will just catch up to us. So in here we can now see that I3 is also equal with I total, which is 3 amps. Okay, and then since we already have the value of I3, so we can now solve for the value of VR3, or the voltage drop across R3. So VR3 is equal to I3 times R3, wherein I3 is 3 amps and then R3 is 1 amp. I mean 1 amps. Okay, so in here 3 times 1 is 3 volts, right? So there you go. So at this point, okay, so if you are going to, get the potential voltage, so it's the same process just like what we did a while ago. So in order for us to get the voltage at point A, so we need to get the V total minus the VR3, okay? Wherein V total is 7 volts, and then VR3 across here is 3 volts. Okay, so this will give us a result of 4 volts. So at this point, we have a value of 4 volts. And the same analysis, just like what we did a while ago, since they are in parallel. So R1 has a voltage drop, or a voltage that is flowing in here, which is 4 volts. And the same with R2, which has also a voltage drop, or a voltage that is flowing here, which is also 4 volts. So we could say that VR1 is equal to VR2, which is equal to 4 volts. Okay, so from here we already have the VR1, I mean VR3. Okay, let's write the VR3, which is 3 volts. And we also now have here the VR1 and VR2, which is equal to 4 volts. And then since we already have the value of VR1 and VR2, so we can now solve for the value of IR1. I3 is already here, I1. Okay, so the formula for I1 is VR1 divided by R1. So for the VR1, we have here 4 volts divided by R1, which is 4 ohms. So 4 divided by 4 is 1. So for the I1, we have 1 amp. And then for the I2, okay, so again, since we already have the value of I3 and I1, we can now solve for the value of I2 using KCL. But just to be consistent, we're going to apply the formula of Ohm's law. So I2 is equal to VR2 divided by R2. So VR2 is still 4 volts divided by R2, which is 2 ohms. So 4 divided by 2 is equal to 2 amps. Okay. Let me just remove this one for consistencies, since I didn't put here the units. So we have here 2 amps for the I2. Okay, so let's verify this one using KCL. KCL at node A. So as you guys can see, we have here I3, which is entering this node A, and then I2 and I1, which is leaving, okay, the node A. So I3 minus I1 minus I2 is equal to 0. Or I3 is equal to I1 plus I2. So what is our I3? So I3 is 3 amps. And for the I1 and I2, which they have a value of 1 amp and 2 amps. So 1 plus 2 is 3 amps. So uh, our values of our currents is correct. Okay, so there you go. We now have the value of I1, which is 1 amp, and then I2 is equal to 2 amps. All right, so there you go. So we now have answered all of the individual currents and then the individual voltage drops. And then let's see if we have the same results by comparing that one to this table. Okay, so let me place it right here. So let's just base it right here. So for the total uh, current, so we have 3 amps. Total voltage is 7. And then for the total resistance is 2.33, which is 1. And let's proceed to right here. R1 parallel to R2 is 1.33. And then the voltage drop across R1 is 4 volts. Okay, which is this one. And for the current that is flowing on I1, uh, R1 and R2, okay, that's the combined value of R1 and R2. So 1 amp plus 2 amp is 3 amps. And we have here the voltage drop across R3, which is 3 volts. VR3. There you go. So we have here 3 volts, or you see me, this one 3 volts. And what else? So we have here the current, okay, on the R3, which is 3 amps, and the voltage drop, and then the resistance, okay, which is 1 ohm. And then moving on to the R2, so we have here a voltage drop, which is 4 volts. There you go. And then 2 amps for the R2 or I2 right here. And then 2 ohms for its own value of resistor. And then for the R1, so we have here 4 volts, okay, across R1, and then 1 amp across I1, and then 4 ohms on that resistor. So yeah, we have the same results, which is only saying that we've got the same, I mean, we've got the correct answer. So were you guys able to follow on how did we get those values? Okay, very good. What about the others? Okay, so maybe at least half of you are able to get it. So again, if you have a question, so feel free to ask me anytime. All right. So once you already have the results in the first set and then the second set, then you can now combine them. Okay. Again, once you combine them, we call that one superimpose. Okay. So by superimposing, so when superimposing these values of voltage and current, we have to be very careful to consider polarity of the voltage drop, okay, and direction of the current flow as the values to have to be added algebraically. Okay, so in here, in order for us to compare it as clear as possible, so let me just get this table right here. So that is the reason why they are in table, to easily compare and add them together. Put it right here. And then here's the second table. And for the superimposed values, oops, not this one. We have this one. So this one is only for the voltage. So we have another table for the current. But let's have the voltage uh, values for now. Okay, so as you guys can see right here, we're going to deal with the final, oops, not this one. Okay, so maybe it's better if we are going to get both of the tables. So we have here for the first table, okay, let me shrink this one. And we have here the second table. Anyway, so I hope you guys can still see this one. So one thing that you guys need to check is the polarity. So notice that we have here positive, negative, and then we have here negative, positive. So if you guys are going to take a look on this one, we have a current that is, flowing in the side, and then we have a current that is flowing on the side. So upon, meeting on the middle, okay, so you guys already know that they will not be added to each other, okay? So there will be a collision wherein, of course, whoever, the larger values will dominate that path or that node. So it's quite obvious already. So it is the B1, or the left side voltage, that is the one that is going to dominate the entire flow of current. Okay, so that is why I've got, if you're going to compare it right here, we have here positive 24 volts, and then we have here minus 4 volts. So how did we know that, it's 24 minus 4, or not 4 minus 24? So one rule of thumb, when it comes to voltages, so it's always the higher voltage minus the lower voltage. So assuming that, both of them have a positive polarity, or positive signage. Okay, so it's always like that. Higher voltage minus lower voltage. So in here we have 24 volts. I mean, not 24. Is it right? Yeah, 24. So we have here 24 minus 4 volts. Okay. So there you go. Having this 124 minus 4 is equal to 20 volts. So, the one that, dominates this uh, node A right here is the left side, wherein the final circuit, I mean, the final value of this one is 20 volts. Okay. So the same with the ER2 and ER3. Okay. So for the ER2, we have here 4 volts, and then for the R2, we still have 4 volts. But if you guys are going to take a look on this one, so our current on, where is this one? Okay, for the R2, okay, so on the left side, we have this current flowing right here, and then on the right side, we have this current flowing right here. So they have the same polarity. So positive, negative, positive, negative. So from here, you could already see that they will be added with each other. Okay. So from here, so R2 plus R2. So you don't need to, see the outer sign, or the entering sign of that one. So it's always positive. We don't have a negative voltage. Okay. So it's always positive. So in here we have 4 volts plus 4 volts is equal to 8 volts. Okay. And then for the ER3 right here, so we have here 3 volts, and then we have here 4 volts. So again, the same concept. The higher the voltage, it is the one who's going to dominate the path or the branch. So we have here 4 volts minus 3 volts is equal to 1 volt for our RT. Okay, so these are now the final values for our R1, R2, and then R3. Okay, so if you guys are going to get the final circuit for the voltages, we have this one. Let me just shrink this one and fill it right here. Okay, so we still have the 28 volts and then 7 volts, but once you're going to combine their voltage drops, we have here 20 volts. Where is that? 20 volts for the R1, and then 8 volts for the R2, and then 1 volt for the R3. Okay, so this is now their final voltage drops, okay, or the voltage across this entire circuit. So were you guys able to follow so far? Okay, Okay, so let you guys, take a look on your screen and then analyze everything. Again, to avoid confusion, all of their values are positive. Okay, so the one that we are considering here is the flow of current. So if they have, different flow, so of course, whichever, uh, whichever is higher, that is the one who's going to dominate the entire flow of current. Well, that only happens on our R1 and R3. Okay, so any questions so far? Anyone? So feel free to raise your hand. Okay, so one more time. So just give me a thumbs up if you guys were able to get it. Just to let me know how many of you were able to follow up to this point. So 1, 2, 3, 4, 4 only. 5, 6, 7, 8, 9. Okay, so 9 out of how many? 9 out of 15 or 9 out of 14. Anyway, so again, I hope to the others who still wasn't able to follow, I hope you at least get the idea and then just review this one, once our discussion is over. So that's it for the voltages. So let's now proceed to the current. Okay. So let me just erase this one. Coding this one. Okay, and let me get this one. All right. So the same method. So we have the IR1 right here, the final current on R1, the final current on R2, the final current on R3. So if you're going to start with R1, so it's very obvious that we have, different polarity. So we have 6 amps going here and then 1 amp going here. So it is now obvious that, whichever the one is highest, okay, is a one, higher rather, not highest, higher is the one who's going to dominate the flow of current. So IH minus IL. So in here we have 6 amps minus 1 amp, which is equal to 5 amps. Okay, so this is the answer for the I1. Okay, so as you guys can see right here. And then for the R2, so it's noticeable that we have the same flow of current, so they will be added with each other. So we have here, so R2 is 2 amps, and then I2 on the other side is still 2 amps. So 2 plus 2 is equal to 4 amps. Okay, so I hope there's no problem when it comes to R2. But for R3, so again, they have different flow of current. So one is going on this side, and then another one is going in from here to there. So in here we have, where is our R3 and current? So we have 4 amps for this left side, and then 3 amps for the right side. So 4 minus 3 is equal to 1 amp. Okay, so that's how we've got those results. All right. So I hope you guys were able to get the idea. Okay, and then also the final currents. So are we clear so far? So just give me a thumbs up if it's okay, or if it's no, just raise your hand. Yes, Mr. Awas, if it's the same direction, add. If they have different direction, of course, this will be applied. IH minus IL. Okay, so of course the value of this IH is positive, and then the value of this IL is also positive. So you don't need to worry about the the signages of these values. Everything is positive. Okay, so that is why it is highlighted in here that we are only talking about DC network analysis. So in DC we don't have negative currents. Okay, so that will only happen in Kirchhoff's law, since we have a different assumption when it comes to polarity. But in reality, that is positive current and then positive voltage. Okay. Well, we're only going to have a negative value of current and voltage if we are dealing with AC analysis. Okay, but since we are only dealing with DC, so it's always a zero or above, zero or positive only. Okay, so negative, no negative uh, values of currents and voltages. Okay, so here is also the final circuit flow of current. Okay, so we have 5 amps right here, 1 amp right here, and then 4 amp right here. So it is now obvious that this 28 volt will dominate this 7 volt right here, wherein is now like this 7 volt is being charged by this 28 volt right here. Okay, so there you go. This is now the final superimposed values for current and then for the voltage. Okay, and yeah, that is actually the simplest example, okay, that I can give to you when it comes to superimpose. So if you want to learn more about position theorem, so feel free to visit these two YouTube link. Okay, so this will give you more explanations, more examples, okay, to learn more about superposition theorem. Okay, and then here's just the summary and the review. So superposition theorem works only, okay, for circuits that are reducible to series parallel combinations. For each of the power sources of a time, thus this theorem is useless for analyzing an unbalanced bridge circuit. So if you want to solve unbalanced bridge circuit, so you can use mesh current method or the Maxwell loop method. Okay, and it only works where the underlying equations are linear. Okay, so that is their main differences. So if a circuit cannot be simplified using Ohm's law, okay, series parallel connection, then you have to use a mesh current method or the Kirchhoff's law, either of those two. But if it's if it can be simplified uh, they using a series parallel connection, and then it has a lot of voltage source or current source, then you can use superposition theorem. Okay, so that is the limitation when it comes to superposition theorem. Unlike in mesh current method, you can solve anything. Okay, so the requisite of linearity means that the superposition theorem is only applicable for determining voltage and current, so not power. Okay, so we can only solve the voltage, or the individual voltage and then individual current, okay, using the superposition theorem, but not the power. Okay, that is why we don't have an example when it comes to solving a power in superposition theorem. Okay, so being nonlinear, functions do not algebraically add to an accurate total when only one source is considered at a time. Okay, so the need for linearity also means this theorem cannot be applied in circuits where the resistance of a component changes with voltage or current. Hence, networks containing components like lamps, incandescent or gas discharge, or various varistors could not be analyzed. So the same with capacitors and inductors. So superposition theorem can only be applied if we have linearity. So when say linear, so it's 1:1. So if we have a raise in current, the voltage will also go up. But if we have capacitor, so even though you're already raising your voltage, but the current is still the same. So that is not linear anymore. Okay, we call that one non-linear. So if you want to learn more about linearity, okay, so feel free to search on YouTube. So it might explain it to you in 1 to 2 to 3 minutes. Okay, or to make it simple, when we say linearity, so we only have these three components, okay, that we could consider: the voltage source, okay, the current source, and then the resistor. Okay, so if we have capacitor, inductor, and any other component which is not linear, okay, then that one is not linearity anymore. Okay, so take note, we only have three components when it comes to linearity. Okay, resistor, voltage source, and then the current source. Okay, so I hope we're clear with that one. So any questions so far? Okay, so yes, no question. So another prerequisite for superposition theorem is that all components must be bilateral, okay, meaning that they behave the same with electrons flowing in either direction through them. So when I say bilateral, okay, so if you guys are going to take a look on this one, what we did in here is conventional method. Okay, the same with this one, conventional method. So if you're going to solve this one using electron method, okay, so it's the other method, so it's counterclockwise. Okay, the same with this one, it's now in clockwise. So it should give you the same result. Okay, because if not, then there must be something wrong with your solution or your answers. Okay. And the superposition theorem finds use in the study of alternating current (AC) circuits and semiconductor amplifier circuits, where sometimes AC is often mixed, superimposed with DC. Okay, so yeah, you can also use superposition theorem as long as it's only pure AC with no capacitor and inductor. Okay, it's just that we have a sine wave instead of a direct current. So you can also apply superposition theorem. Okay, so just a review again, the superposition theorem states that a circuit can be analyzed with only one source of a power at a time. So the corresponding component, voltages and currents algebraically added to find out what they'll do with all power sources in effect. So to negate all but one power source for analysis, again for the voltages, replace any sources of voltages or batteries with a wire or just short it. Okay, and then for the current source, replace any current source with an open break, okay, or just break it. And then here are the references for this presentation. So we have three. One is for the all about circuits, which all of the information right here came from this website. And then we have another two related references. So just in case this explanation that came from all about circuits is not enough, feel free to visit the tutorials point and then the circuit globe. Okay, so they have another approach, another way of explanation, okay, in which it might enlighten you to understand more about superposition theorem. Okay, so yeah, that's it for the superposition theorem. So are we clear so far? So just give me a thumbs up if everything is okay. Okay, okay, okay. All right, so very good. So please half of you. How about the others? Okay, so I have mentioned that it might only took us 2 meetings, but it seems that we might uh, not be able to finish the module 5 and 6 with 2 meetings only. So we have to extend up to part 3. Okay. So anyway, without a further delay, let's now start with the revised module with the module 6, which is a nodal voltage analysis. So don't you guys worry. If superposition theorem is already easy and simple, though it's only uh, time uh, allotment, so you need to allot of time because you have to solve if you have three sources, then you have to solve three set. If you have four sources, then you have to solve four set also. Okay, but in here, in nodal voltage analysis, so it's only one time. Okay, one time big time. So in nodal voltage analysis, so we are dealing with nodes. So we have VA, VB, VC, and then VD. Okay, so the same things that we can find on the superposition theorem. We can also find the individual currents. We can also find the voltage drop for the R1, R2, and R3. Okay, it's just that it has its own analysis and ways of solving things. So nodal voltage analysis finds the unknown voltage drops around the circuit between different nodes that provide a common connection for two or more circuit components. Okay, so let's have this example as as our basis in solving nodal voltage analysis. Okay, but before that, let me just clarify things. So if in a superposition theorem, we are applying KCL, we're applying series parallel law, the Ohm's law. In here, we are only applying KCL and then Ohm's law. Okay, well, to be exact, as long as you know the KCL, that's already enough for you to be able to solve the voltage or nodal voltage analysis. Well, of course, with a little bit help of Ohm's law. Okay, so nodal voltage analysis uses the nodal equations of Kirchhoff's first law or the KCL to find the voltage potentials around the circuit. So by adding together all these nodal voltages, the net result will be equal to zero. Okay, so from the first node to second node to third node and so on and so forth. So at each node point, write down Kirchhoff's first law equation. That is, again, in first law, the current that is entering a node are exactly equal in value to the currents leaving the node. Okay, positive for the entering and then negative for the leaving. Okay, then express each current in terms of the voltage across the branch. For n nodes, one node will be used as a reference node, and all the other voltages will be a reference or measured with respect to this common node. Okay. All right. So let's now start with this example. So what I will do is I will get this one now and then have our own solution. So uh, in this presentation, it has its own solution. Okay, but in my case, I will just explain from the very start so that we can understand everything step by step. Okay, so in nodal voltage analysis, so this one is super simple actually. All you need to do is apply KCL at node VB. Okay, so in here we have I1 going in. So I1 positive and then I2 going in or entering. So it's plus I2. But in here we have leaving. So minus I3 is equal to 0. Okay. So this is very, very important. This is now your basis or reference when it comes to solving for the unknown variables. Okay, in this current. I mean in this circuit. Okay. So let me just recall or write here the Ohm's law. So I is equal to V divided by R. Okay. So the same concept with this one, wherein I1 is equal to the voltage drop across this one, VA and VB, okay, divided by R. Okay, so let me just write down again the rule, okay, when it comes to getting the potential voltage. So we have here the VH or the higher voltage minus the VL, okay, for us to get the VR1 or the voltage drop across that R1, okay. So in here, the same method just like what we did a while ago, we could have here VA minus VB, okay, is equal to VR1, okay. So again, how did we know that VA is the higher voltage than our VB? Because we have this flow of current right here. Okay, assuming that we have 10 volts right here. So of course, after passing through this voltage drop, then we now have a lesser voltage at this point at node VB. Okay, so that is why we have here a expression VA minus VB. Okay, so in here we're just simply going to put it right here as our for the voltage. Okay, the final voltage across VB. So we have here VA minus VB, okay, divided by R. So what is this R? Let's just name this one as our R1, R2, and then R3, okay, divided by R1. So there you go. That is now our first expression for the I1. Okay, so since we don't have enough time again, we will just continue the rest on part 3. So again, goodbye for now and see you guys later on part 3.